All right, so we are done. We got our projects. Hopefully today we'll get the evaluations. I want to cover, I answer questions, but hopefully that first 12 minutes that we had before we started the video was helpful for the final exam. Yeah. Okay, just checking. All right. So let's go back and see what lecture we have. Just so everybody knows, we'll review for the final on Thursday. Today I'm going to talk about other op-amp topology. Since it's all fresh in your mind, I want you to have some thoughts on how you solve problems just in case you get a job working as a circuit designer, which likely would mean you have to move, but that would be horrible. All right, so today's lecture 28. Write that down. It's hot in here, isn't it? So today's May 3rd. So projects weren't overwhelming?
Not particularly, no.
They were easy? Yours was?
Just a lot of work for me. Long days. Tomorrow.
You got another one due tomorrow? Oops, are we recording? Yes. Oh yeah, for the senior design. All right. We'll make sure that I come and check out your project. And ask lots.
We got other ones there too, so.
All right. Okay, so any questions on the, and everybody saw when the final is. It's a week from today. It's Tuesday the 10th. Where was it? Tuesday the 10th, 10:10 to 12:10 in this room. Open book, closed notes. We're going to cover what, I'll probably write it up before Thursday. So when I give you advice on what to study, you're getting good advice. Unless you don't want that and just, I say, study everything. That would be better. Yes? Okay, we'll do that. Just kidding. All right. So I wanted to talk about specific, well, before I do that, are there any project questions that you are working and you're like, I don't know what's going on. What's this? What's up with this? Everybody understands their projects? Warku. So when I ask you questions on the final, you'll be like, that one was easy.
I have a question.
Lay it on me.
So to push out the F2 or whatever.
Push out F2.
Yeah, I was upping my input width.
No, you up the widths of the transistors on the output stage. So that will keep the VGSs constant, increase the current that flows in those transistors, and push F2 out. The input diff pair, if you make those wider, that increases GM1, which pushes the unity gain frequency out. I think you want to put modest, like maybe up to 4 in the input diff pair, and then in your output stage you might go 20, 30, or even wider. Okay, so let's start. Let me ask you a question about that before I get on. I want to cover a voltage regulator topology today. So let me ask you the following. Let's say that you're designing an op-amp that needs to have a good, be able to respond to a pulse. And you look at your output, or we won't worry about what the deal is there. We'll just look at the output stage. So here's your output. And I'm coming over here, and I've got my, what do I connect that to? Yep. And then I come over here, and I connect that to. Is everybody cool? So if I ask, what is VNCAS, what is the answer? And what is VPCAS? Is everybody cool with that? So now I ask you, I want to make these guys really wide. So say I said M equal to 1,000. They're huge, and I don't need a compensation capacitor. Is everybody cool with that? What's the issue if I do that? Yeah, I'm going to get a lot of current, right? This is I bias. This will be 1,000 I bias. So if I bias was 10 microamps, and I have 1,000 here, these burn 10 milliamps. Now there may be some situations where you want to do that because the GM will be really high and you can drive a heavy load. So what's the GM of this stage called? In our little node 1, node 2 compensation stuff? GM2, right? The diff amp's the GM1, and the GM2 is equal to GMP plus GMN. I'm sure I'm going to see that on all of your projects. Because Co said the projects are easy, so I'm having high hopes. All right. So now, let's say that I only have this large bias current because I want to be able to supply a large pulsed current, meaning I need to have M equal to 1,000, but I don't like the fact that I've got such a huge current flowing in those devices. Tell me how to modify the circuit to reduce the current flowing in the output stage so that it still has wide devices that I can pulse and supply a lot of current, but I have a smaller DC bias current.
You make your floating ones smaller.
Yeah, I make these weaker, right? Does everybody see that? So this would be a question I would, and so what do I mean by weaker? Reduce W over L. Increase L or reduce W. Okay, so that would be a question I would ask. I'd put the circuit on there and I would say, how would I, from a DC biasing point of view, reduce the bias current that flows in the output transistors? Yes? Okay. Wait, if I reduce this width, here's plus minus. If I make W over L smaller, what happens to this voltage for the same bias current flowing through it? Goes up. Because if I make this weaker, it's got to take a larger VSG to drop the same current that flows through it. That makes the voltage that's left, because this is still staying VDD minus 2 VSG, it makes the voltage left to drop across this one smaller, so it shuts it off. Same thing here. This is still 2 VGS, so I get a voltage here, which is VGS, voltage here, but if I now make this a weak device, my VGS here goes up because to get the same amount of current, I have to have a larger VGS. I have to turn it on more. So that leaves less voltage to be dropped across there and shuts it off. Okay, so we've done that. We have big devices. We're not burning a lot of current, so we can supply large pulsed amounts of current. What is the issue with doing this? What is that? Nope. What's that? So if this goes towards the threshold voltage and this goes to the threshold voltage for small signals, that means this can go basically to VDD and can go to ground. What happens if you reduce the current flowing in these? Wait, I'm the king of repeating myself. Well, so what was the first thing we went over today? What's that? Yeah, F2. So if I reduce the current here, what happens? F2 goes down, and it can interfere with the regular compensation. However, I've increased the widths quite a bit, so that's going to cause F2 to stay high. So I can have a reasonably large F2 still with a wide device and smaller currents. So I know F2 is proportional to GM2. So I know causing VSG and VGS to go down causes GM2 to go down, which causes ID to go down. However, if I make M go up, that causes GM2 to go up and I to go up. Does everybody follow the trade-off you'd have to make? If you use really wide devices, you know, hey, I don't need to have a compensation capacitor there because the devices themselves will compensate the circuit. All right, any questions on that? Are you sure you can answer questions on this on the final exam?
You're saying making it wider, you're talking about the, floating?
M equal 1,000. So, I was going to say, if M is 1,000, it's 1,000 times wider than the other transistors in there, right?
So what other questions would you ask?
Is ID directly related to F2, or is it just related
Yeah.
through GM2?
No, ID is directly related to the GM2, right?
To GM2.
Yeah, it's, let's write the equation.
Oh, that's
GM
it's directly related to F2.
ID?
ID.
Well, it's the root, right?
Okay.
Yeah, so it's 2ID times KPW over L. So you're reducing the ID, but you're jacking up the W over L.
Gotcha.
So same thing with this. GM equals KP times W over L times VGS minus V threshold in. So the point I'm telling you this, and I don't want to, you know, when you do your projects, I don't want to throw too much at you, but the point is, if you get a job and you're designing power amplifier circuits and you need one that can supply a lot of current, you can choke off the current in here by increasing the size of these, which will, but on the same hand, and then make these larger devices, they can supply more current. Okay, question? All right, so what I'm going to do now is I'm going to go over a design that I did that's on a lot of products. That's a voltage regulator that's an op-amp design. And I want to motivate, I want to provide a motivation for why we have to do what we have to do. So I'm going to draw the box here, and there's an op-amp in here that's regulating. So there's a band gap coming in, or maybe inside, voltage regulator. And that comes out and goes to a load, RL, and this is my V, we'll call it V-reg. Okay, so this is a voltage regulator. I got my power supply, my external chip, VDD, and then this might be the on-chip power supply. And I want you to tell me, talk to me about this. So let's say this is I did this design on a DRAM. Let's say that I need, for a very short period of time, I need 1 amp of current for, let's say, 5 nanoseconds. And you say to me, wait, there's no way you would need that much current on a DRAM chip. Well, if you're opening a row of memory, or you're doing something with thousands of things at the same time, you get switching currents. The switching currents pull a displacement current, and you have to charge and discharge capacitors. So I want you to tell me, if I do this, I pull 1 amp of current for 5 nanoseconds, and you imagine in your op amp you have the following. Let's just say you have, let's just say the following. 10K. Did anybody take their op amp and put it in other topologies besides a follower to have fun? Well, it's a real op amp. You can now take and put it in a gain of 2 or whatever, right? This is a Bandgap reference. We went over theirs, BGR, and it puts 1.25. And now I'm going to pause and hopefully not cry. What's the output voltage? What's the gain of this? Anybody not look at this and immediately see gain of 2? 1 plus RF over RI, non-inverting op-amp burned into our brains. Okay? And I have my power supplies going in, and my power supply might go from 3 to 5 volts, or maybe even beyond, say 3 to 6 volts, and you say, hey, no problem. I can supply 2.5 volts. This is a voltage regulator. Sound good? So this is my voltage reg right here. And you say to me, okay, what's the problem? In your op-amp designs, if you pull 1 amp of current for 5 nanoseconds, what do you think is going to happen? And if you disagree with me, go home and try it out. What do you think is going to happen when you pull an amp of current out of that op-amp in 5 nanoseconds? It's going to die, right? It's going to pull that node to the ground or beyond if you put an ideal current source there, current pulse. You're pulling out a whole bunch of current, but there's no capacity, and you're doing it in 5 nanoseconds, so the op-amp can't respond and turn on in that amount of time, right? There's a finite time that it takes to feed back around and turn the device on. Does everybody see that? So what you say is, okay, what do I do to supply 1 amp of current for 5 nanoseconds? This is a real problem. Real chips. What do I have to do? You have to put a capacitor there, right? And now I'm going to pause and we're going to calculate the size of the capacitor ourselves. See coupling. Rudy?
So what the capacitor does is that basically it holds a bunch of charge because we charge.
Yep, it's a holding tank.
And that 1 amp will just take out, most of the current from the capacitor, right?
Yeah, so in this short time, the op-amp really doesn't do much. The charge all comes from the coupling capacitor. Let's just call it C coupling capacitor, CC, so it's not the same as C compensation in the book. Sound good? Okay, so let me ask you this. These are some fundamental circuit questions. Can I supply 1 amp of current for 5 nanoseconds if the voltage across the capacitor doesn't change? No. Okay, you need to understand that. When you put that big capacitor there, the only way that thing's going to supply charge is if the voltage across it changes. Does everybody get that? Okay, so now the question is, how much of a change is okay? There needs to be some change. Can it go from 2.5 to 2.1? Can it go from 2.5 to 2.45? What is a reasonable amount of change?
Doesn't that depend on the size of the capacitor?
Well, it depends on your application. We're trying to figure out how to set the size of the capacitor now. So I'm going to say that we're going to pick the size so that the capacitor changes, or the voltage that we're regulating goes from 2.5 to 2.45. And you need to understand this. When you're designing a power supply, when you have sudden changes in the current that's required, you're going to see a sudden change in the voltage across the coupling capacitor. That's why we have these on every device when we do PC board design. You do a PC board design, you don't put a coupling capacitor on your chip, it's not going to work well because you're cratering the power supplies on your chip. So if you look in any commercial product in chips, there's always coupling capacitors either under them or adjacent to them. Always. And it's capacitor from the power supply to ground, and as close as possible to the power supply ground.
On like boards and stuff, when they do that, would they put the capacitance like in the actual board, not just like,
Sometimes they have capacitors because they're trying, like on your phones and stuff. They'll use capacitors they'll place underneath packages or above so that they're harder to see. They won't use discrete capacitors like you would in like your senior design project or something, right? So they're trying, but you need to have them. In fact, nowadays, they'll have on-chip coupling capacitor, decoupling capacitors, off-chip decoupling capacitors, and they'll have lots and lots of pins for supplying the power so that you can put more capacitors at different places to make sure that there's plenty of charge available to source the needs. It used to be back 20 plus years ago that you'd have one power pin and one ground pin in like a commercial memory or a processor or something. Now the power and ground pins practically outnumber the signal pins because of this issue. Okay. Alright, so tell me how to calculate the size of the capacitors, knowing that I only want my capacitor to discharge from 2.5 to 2.45. Okay, so here's what's, I'm going to tell you my thought process. This capacitor's got to supply a chunk of charge. What's the chunk of charge it needs to supply? On these, I always start out CV equal Q, right? I write I equal Q over T. What do I use? How about, well, I could, I'm going to do it a little slower. So the amount of charge that I need is I times Q, which is 1 amp times 5 nanoseconds, or 5 nanocoulombs. My C times my delta V has to equal 5 nanocoulombs. My delta V is 0.05 volts. And my C is equal to 5 over 0.05 nanofarads, which is 100 nanofarads.
Really close. I was gonna say, I was just off by a magnitude of 10.
All
Just
right.
1 inch short.
100 nanocoulombs. Does everybody agree with that? Okay, so now you have a feeling. You did your op-amp projects. That's a huge capacitor. That has to be off chip, right? You're not going to get that on chip. What if you put 100 nanocoulombs on your op-amp outputs? How good's your op-amp going to work? Is anybody's op-amp going to work with 100 nanocoulombs on its output? Yours will? No, I want you to go try it. Do a step response, put 100 nanocoulombs on the output, do a nice slow step response so that you don't have to worry about the time, like microseconds, and then look and see how stable it is. Okay, does everybody follow that? Okay, so I'm going to talk about how to design the op-amp when you've got a large, because you need that. There's no way the op-amp can supply the charge needed. You have to have a compensation capacitor. But I'm going to give you a quick problem, and I want a thought problem, and I want you to tell me what the solution is. Okay, this is related. So, now? When I first started teaching back in the early 90s, I taught a lab. And I walked in, and part of the lab was an op-amp project. And the students had an op-amp like this. And they put a voltage source here, let's just say 2 volts. Then they took, and they had a meter. And in the meter, they took a cable, and they put this is a cable. And they put the red lead to the output of the op-amp. They put the black lead to ground, to measure over here. So they're varying this voltage, they're taking 2 volts, and they're measuring the output voltage of the op-amp. Does everybody follow that? So if there's 2 volts here, what should there be here? 2 volts. If I change it to 2.5, of course I'll measure the offset, right? Easy problem. And students came to me and they said, hey, when we look at our meter, it's hopping all around. It's not steady. I'm not measuring 2 volts. Sometimes it's 1.5, sometimes it's 2.7, sometimes it's 2.1, sometimes it's 0.7. Why aren't I measuring the voltage right? What's going on? Yeah, the capacitance of the cable is loading the op-amp and making the op-amp unstable. In fact, in your designs, you can put a big capacitor on the output, do your step response, and it will oscillate. So when you get oscillations, you'll know that, hey, this is an issue. So tell me, without doing any direct, does everybody follow that? when you see oscillations, you go, okay, I put too much capacitance on the output of my op-amp, it's oscillating. It's a feedback circuit. Where did I get that capacitance from? Oh, coax has got 30 picofarads per foot. If I put 10 feet on there, that's a 300 picofarad capacitor. That's an issue. Tell me quickly how, I don't want to change my setup, what can I do to the circuit to make it so it's stable? And I'm going to give you a hint. If I look this way with my little eyeball there, and I ask, what's the DC impedance I measure looking into the red lead? What's the DC current that flows looking this way? Of course, coax, you know, is a wire in the middle, goes over into your meter, and then there's the shield, which is a conductor, which goes over to the other prong. So this would be a banana plug, which would be a red and a black banana plug. When I say banana plug, everybody knows what a banana plug is, right? What's a wire nut? Wire nut.
It's a nut you screw on the
Yeah, it's the nut you screw onto the, yeah. Yeah, somebody says, where's the wire nuts? They're the little twisty things you put on the end of the wire. All right. So what's the impedance I see looking in there? It's infinite, right? I mean, it's 100 meg. It's really big. So how much DC current does the op-amp supply? Very little. Does everybody know the input impedance of a meter is like 100 meg, right? It's not magic. It's set to 100 meg. So that when you put a high voltage probe on there, if you're doing high voltage measurements, you can get a voltage divider between the high voltage probe and the input impedance of the meter. Just like what's the impedance of a scope? 50 ohms or 1 meg. You know that, right? This should be in circuits too. You should be doing all kinds of crap with your equipment to find out what the limitations are, so you know when you stick it in your circuit, it doesn't mess your circuit up. What do I know?
Probably when everybody burns up everything in the power.
Yeah.
You teach it circuits 1 next semester, right?
Yeah.
I'll see that.
Well, there's no lab with circuits 1, so it's going to be like how to. It's going to be one thing. It's going to be lots of is this. 5 divided by 0.05. Come on. Come on. In engineering units, that should be like trivial to you. Divide top and bottom by 5. That's 1 over 100. Flips up.
You know, you can take them on field trips. Look at this side.
Nah. Tell me how to modify the circuit so that this meter stops oscillating. I gave you a hint. No. This is an op-amp. I don't have a compensation. It's inside the chip. What do I do? Put a resistor here? Put a resistor here? What do I want to remove from the op-amp? What's causing the problems? The capacitance. Okay, if I'm sitting in a room, and if I'm sitting out on the open field here, whatever we want to call it, the concrete out there, and someone starts playing some music, they start playing some country music I really hate, all right? And I'm saying, I don't like that song. How do I get rid of it? I put some resistance between my ears and the music, right? So what do I do here? I put a big resistor there.
That's what I said.
You did not. You said a resistor in the feedback, and then you said resistor shunting.
She said resistor shunting.
Okay, does everybody see that? So now, that's an RC circuit, right? Still lets the DC go through, that's what I'm trying to measure, but it puts enough of a load there, I put like 100K or whatever, and it isolates the capacitance from the op-amp, and no longer will it oscillate. You see how you're thinking? Earplugs. Questions? Okay, so now you'll seem smart because you'll have this experience when someone says, why is my circuit oscillating? Let me see. Oh, you got a cable there. That's a lot of capacitance.
Just hang this resistor right there.
especially if you have level or pool problems. You'll really be smart. They'll be like, those things shut off after 20 minutes of being on. You have to open them up and set the time they stay on. What's sad is in 5 years I'll probably have forgotten, have to relearn it. Anyway, so now I got a big capacitor. What I'm going to do is I'm going to design the circuit so that my circuit can supply a lot of, so that it's compensated with the load capacitor. Because the bigger I make this, the more stable my circuit will be. Okay, so I'm going to give you some examples. Let's say that I put and now you're all familiar with this, let's just say I do the following. What is this topology? Oops. Folded cascode, right? And you say, that's what I'm going to use. I'm going to put my, whoops. I don't know if I put negative feedback on there, but whatever. This is the circuit I'm going to use. What's the problem with doing this for my voltage reg? What's that? Yeah, but it's a OTA. It's one stage. The bigger the capacitance, the more stable it is. What's the issue? I try to do this. I've done this before. I've been in design. I'm like, well, I try a folded cascode, and then I realize, hey, stupid, that doesn't work. Here's why. But making mistakes is good.
Is it because the output is still regulates the input? Like if you're trying to regulate the voltage, when it's still.
No, I just say this is 1 point. It's the same circuit. 1.25. Here we can do 10K, 10. It's because the output impedance is high. When I put 20K on the output, it kills the open loop gain. In a feedback system, remember it's AOL divided by 1 plus beta AOL, or 1 over AOL plus beta. Here beta is 1/2, so the gain is 2. And if I have AOL as a huge number, then it works fine. If I put resistors on the output, I kill AOL, and it doesn't work. Everybody follow that. So then you say, well, that's the whole point of us putting the second stage on. If I put the second stage on, let's say that I put in here a source follower like this. What's the problem with this? So I insert this source follower in here. Okay, what's an obvious issue, because we already talked about this when we were going through the designs? Well, remember the circuit's only sourcing current. It doesn't need to sink current. So this, we can make this guy big, and it can source all kinds of current. It turns on, sources it to the load. What's the I'm asking a trivial question. You know this. We've already gone over it. It's the whole reason we went to the inverter on the output. Push-pull. Output swing. Does everybody see that? This guy can only go up the VDD, but as the output goes up, it doesn't let us get a big VGS here. We need a big VGS in order for this to supply lots of current. Is everybody cool with that? Kind of shuts itself off, so as the power supply drops, we get less VGS, and this has to be huge. And we don't get good output swing, so we can't go as low with VDD as we want. We want to go as close to 2.5 volts for our VDD as possible. Then the circuit is more robust. Okay, so now what about the class AB stage you used? We could just plot that in there, wouldn't that work? Well, wait. If no, without another diff amp. Just say that this is always, we wouldn't need another diff amp because we know the input common mode voltage is always going to be 1.25 volts. It's going to a band gap. So we need 2 diff amps, right? So what's the problem with putting the class AB in there? What would be the problem with putting a 100 nanofarad, 100,000 picofarad, a 0.1 microfarad capacitor on the output of your designs, even if you played around with the widths? It'd move F2 way, way, way down, and it would still be unstable. Does everybody see the issue? So I need this capacitor to supply lots of charge, but if I put it on there, there's no way for me to do dominant pole compensation or 2-stage op-amp and design things like that. So here's what I'm going to try. And you're going to tell me what the issue is. I'm going to do this in stages. Good test question. Did this semester go by fast? A little too fast, way too fast. Okay, so I look at this and I go, all right, let's first off ask which is the positive and which is the minus terminals of the op-amp. So this side goes up, this goes on, this goes up. Yay, you learned something in your projects. This is the minus side. How many high impedance nodes are there in here? There's this one, and then there's our inputs, correct? Okay, so if I put a resistor coming back here, and I go do this, and I put it in the topology where we have a gain of 2, what's the issue? You kill your open loop gain. So here's what I'm going to do to avoid that problem. I'm going to make this guy really wide. Does everybody see that? If I do that, what does it do?
Well, you source more current.
Yeah, it sources more current. Allows the output to drive a resistive load. And we're running out of time, so I'm going to point you to what we're going towards right now. And we're going to do which is the following. Okay, so wait. So let's make sure before I put this up. If I only have one node, so even if I make this really wide, the issue is what? Well, to get high gain, right? I need high gain. Does everybody see that? So it would be nice if I had a 2-stage op-amp. So here's the topology that I went with in the book. And I want to just discuss this for a minute. And I want you to look at this and tell me which is the circuit we just talked about. This stuff right here, right? But wait, I have now just a common source stage, and I make this M7 really wide. and I have my compensation capacitor there, but as we know, we can't compensate the op-amp with that there, and if you go through the discussion, it actually makes the circuit less stable. So why do I have this capacitor there? So imagine, so I'm compensating, I put a huge CL there to compensate the op-amp. Okay? Now, if all of a sudden Vreg starts to drop, imagine this is a practical circuit. This Vreg starts to go down. It goes down 50 millivolts. I want all of my charge to be supplied by that guy, right? But tell me what happens. If this node drops a little bit, that compensation capacitor is still there. It feeds into the gate here. So if this node voltage drops, this node voltage will drop by 50 millivolts. Tell me what happens then. It turns on and starts supplying the charge. So we have two things here. We have a capacitor to supply the fast charge, but if this node starts to drop, we put this compensation capacitor here so that the signal feeds through the gate and turns this on and allows the extra charge to come out here. Now note, we have a compensation capacitor here on chip. We also need, not compensation, we have a decoupling capacitor here on chip. Notice there's no magic. This also has to have a really good decoupling capacitor on it to supply the charge when M7 turns on. Does everybody see that? Okay, so the issue now is I got to keep the gain of this stage low so that I ensure that F2 dominates is at a lower frequency than F1, because if I make the gain of this stage too high or I make C sub C too high, F1 starts to drop. So in this circuit, I've switched F2 and F1, and I'm compensating with the load. So the heavier I make the load, the more stable the circuit will be. The bigger I make C sub C, the less stable the circuit will need to be, or will be, but it's there because of large signal reasons. The output starts to drop, it feeds through and turns M7 on and turns the device on. So we went through in chapter 24 and we learned how to design op-amps. We had a project, you learned a topology for designing op-amps for most of the situations. This is an example of where you would throw that stuff out the window and you would design an op-amp topology based on ensuring you have good, you can have a big capacitor. Does everybody follow that? Okay, so I got a question. What's the point of using these two transistors here? Why not just use the transistor connection like we had at the very beginning of the class? It's where this node goes all the way over. Here, let me show you. Why did I put these two extra transistors? It's a very straightforward question. Why did I put those two transistors in instead of just using the topology seen right here? What's that? Well, no, this node is still high impedance. Whoops. This node is still high impedance, right? So why not just connect it over to here and make this guy's gate going over like the topology I just showed you? Now I want you to think about, how do I turn M7 on? You pull the gate down to turn it on, right? With this topology, I can pull this all the way down to VDS SAT, right? If I go back to the other topology, this one, I can't pull this down that much. Does everybody follow that? If I can't pull it down that much, this needs to be wider for the same amount of current. If I pull it down all the way to ground or near ground, I can make this guy smaller and supply more current. Any questions? So if I were to ask you some question on this on the test, everybody would be like, oh yeah, that's what's going on. If I asked you, why don't I need 2 diff amps in parallel, what would you say? So that's what your projects were. Why'd you need it there? Yeah, you need a wide swing input, right? Here I don't. The input's staying at 1.25 volts. Common mode range is 0. I just need to be able to handle 1.25. Any last second questions? All right, let's see if we have our teaching evaluation today.